Okay, so here we try to set the position of the vector r vector as x, y, and z. Uh, but note that because we are in the plane of x, y, so here this x is actually 0, and then the velocity of this particle can be described by this 0 y dot and z dot. Now you can we can write down the force along the so the force should be q e plus sorry. And here for the QE, it should be always along the z direction, and for the v cross b, the v cross b can be so the F magnetic is using the, let me see, it's the x, y, z, so it's 0 for the v in the x direction, and then the b is along the x direction. So for this determinant, we only have two terms. One term is along the y direction, so it's b z dot y, and it's minus because it's in the other direction, so it's b y dot z hat. Then let's check here. The QE is along the z direction, so it's QE z hat. And now as we add these two terms together, so they should be equal to the MA, which is y double dot. So my double dot should be bz dot, and z double dot is equals to qe minus by dot. So you see that this is actually a coupled equation between the sys.
I think there will be an additional Q in the mathematical part.
Oh yeah, yes. Yeah, thank you. So there should be an additional Q. So it's Q over here and Q over here. So this is a coupled equation of a function of y and a function of z. So let's try to solve this equation here. So the way we can solve this equation is to do a time derivative on the first equation. So means y triple dot over qb equals z double dot. Now we can use this z double dot and plug in to the equation, second equation. So that gives us m squared y triple dot over qb equals qe minus qb y dot. So we can simplify this equation by to the following. So here this we can let this m over qb equals to omega, and then this will be simplified into omega square y triple dot equals e over b minus y dot. So I guess you are familiar with this kind of differential equations now, and so if you think of this as the equation of y dot, then the y dot must be cosine omega t, and so it can be a arbitrary constant of cosine omega t and a constant of sine omega t, and you have to add additional linear term of e over b, as constant term of e over b. So if you plug in this expression into here, you can see it solves the equation. So we can check. Sorry, I should define this in the sorry. I guess that if we define it in the other way, it can solve the problem. Okay, so say we let omega equals qb over m, then what's over here is omega minus 2, and I think it solved the problem, right? And then this means that y dot equals, sorry, this means y should be minus c1 sine omega t. So y should be a function of sine and cosine and the linear e over b term and the arbitrary constant. So in principle, here the minus sign doesn't matter, and the 1 over omega doesn't matter as well, because this C1 and C2, we can redefine the C1, C2 that is different from the C1, C2 above, but since they are arbitrary constants, so it doesn't matter. Now, after we determine the y, then we can simply determine z, where the z should simply, according to this first expression here, it should be 1 over omega, and integrating over this so this z actually should be y dot over omega plus a constant and another constant, and this y dot is equals to C1 cosine omega t plus sorry, it should be minus sine of C2 sine omega t and plus E over B omega plus C4. So now we have the also have the initial conditions. So here our say that we put the particle at rest. So we start from 0, 0, 0. And we start also at zero velocity. Then we can determine all these coefficients. So finally, I'll simply write down the solution. So now this expression might doesn't ring a bell to you, but we can try to take a more detailed look of this expression. So here we can try to define a constant of R. So say that E over omega B is a constant R, and then we can simplify this equations. Here this y of t is minus R sine omega t plus E over bt, and z of t is minus R cosine omega t minus R. And now you can see that this E over bt is also can be written down as R omega t. Now you can see that somehow this term and this term we can combine them into a motion. Combine this into a circular motion by rearranging these terms to one side. So let's so this term square should be an R square sine omega t square. And now let's add this term to the term over here, and so these two terms combined should actually be R square, because R square sine omega t square plus cosine omega t square should be R square. And now you can see actually that this yt and zt somehow forms a cycle of radius r, and however this center of this cycle is in motion of r omega t. So you can think the trajectory of this charged particle to be a trajectory of a moving circle. Okay, so somehow we finished this. Another thing that I want to emphasize is that the magnetic field does no work. I guess you're already familiar with this in 2041. So to derive this is simple. Here, just to remind you, now let's you think that the in an infinitesimal time, the particle moves to a different direction because of this velocity, and so this dl equal to v times dt, and in this time the work done this magnetic force is F magnetic dot dl, and because this dl is along the v direction, so the this triple product can be rearranged and rearranged to a v cross v. So let me see. So it can be rearranged to the v cross v times b, and this term is always 0. So the final result is always 0. Now here I haven't haven't give you the definition of current yet. So for current, we should think of being a charge, the change of the charge per unit time, or passing a given point as your wire. So suppose that this is a wire, and you have to cut the wire here, and then you count all this current charge that's passed through your surface here per unit time. So the unit of this current is coulomb per seconds, which is ampere. And like these charge in the E fields, so the current here also has different definitions. So sorry, different dimensions. You can have a line current and a surface current and volume current. So here the line current is sorry, it's a bit messy here. So a line current is most straightforward. So you can think of a line current by having a line charge, lambda, and moves with a constant velocity v. And so here, if you use your definition of the dq dt, so here this dq and the q is here the dq dt can actually be rewrite into lambda dl dt. So you can check that the dimension of this quantity makes sense, because lambda is the charge per unit length, and so here the unit of this quantity is coulomb per meter, and then you times this meter and divide by second, so you still get this by coulomb per seconds. So and now for this dl dt, you can actually combine this into the velocity. So that's why here this current can be simply re-expressed as v times the line charge. So whenever you see a line charge that's moving, you can already determine the current simply by using the v times lambda. However, I want to mention that here, because we typically think of line charge as a wire, and the current is simply the amplitude of the current that's flowing along this wire. But because the wire is can have a direction, so you have to actually remember that the current here, I, is also a vector. So for this linear charge, for this linear current, the Coulomb, the Lorentz force should be uh, written as V cross P dq, and integrating over all this charge, and you can again replace this dq by this lambda dl, and this v lambda can be combined into this current. So here, for this linear current, you can actually arrive at the final magnetic field by I cross B instead of Q V cross B now. So the integration should be done across all the wire, and because along a wire the I is typically parallel to this dl, so you can actually move this vector to this dl. So here, this is what I did here. So instead of I cross the B, the dl should cross the B now. And one step forward, because the current is typically conserved or constant along the wire, and so we can pull this I out of this integral, and the magnetic field for this current in a wire can actually be written as this current times the dl cross B. So if you still remember, you have done a simple question like calculating the force felt by a closed loop current in a uniform B field. So can any of you give an answer to this short question? So here the question is, what's the force felt by this current, forced by this closed loop current in a uniform magnetic field? And you actually already done this problem in 2041, so this is just a reminder, so you can try to so the trick in this problem is that I just write down the force here. It's a closed loop integral, and it's dl cross B. So, do you have a guess of what should be the force? Huh? Okay, yeah, the total force should be 0. So the reason is because here, just like how we did to this I term. So because here we see that Ci is a constant, so we can pull this out of the integral. So because here this b is a constant, we can pull this b out of this integral as well. So what we have is the integral only along this dl and cross the b. So then, because this is a closed loop, so this integral inside should be exactly 0. And that means that force felt by this closed loop current should always be 0 in a uniform magnetic field. So let's check another example. So here we are considering magnetic fields B in the shaded region, and it's pointed into the page. So if we draw the sign, it should be a cross. And I hope you know what this cross means, right? So do all of you know what this cross means? Okay, so cross means into the page, and just in case this dot means out of the page. So here we are trying to balance weight using a magnetic force. So now we for here we don't consider the force produced by this two sides, because I think they cancels each other. So say that because the current over here and the B field into the page, then one should be feeling towards the left, and another should be to the other direction, because then these two force on the sides cancels, and the force of this so if the current flows along this line here to the right, then you can calculate the force should be upwards, and according to this, according to the form of F equals QV cross B, and then the magnitude of this force should be QVB, because the B is perpendicular to the current direction. And now this force should be balanced by this mg. So here C sorry, so it should be I it should be the I should be doing, instead of the charge, I should actually use the force of the current. So it should be I times dl cross B. So here this dl along this wire is A, so it should be IA times B. And now this term should be equal to the mg. So here then the current that you need to balance the weight should simply be mg over A times B. And now imagine that what happens as you increase the current. So in this case, this mass will move upwards, right? So does it mean that the magnetic force is doing work? So my question is, say here we calculate the balance condition, and at the magnetic at the current where it's equal to mg equal divided by a times b, then the force balances. But if we increase the I, then the magnetic force will be larger than uh, this gravity, so the mass will move upwards. But does it mean that the magnetic force is doing work?
No.
Yeah, so from the principle that magnetic force does no work, it means that it has to not doing work, right? So how do we understand this problem then? So the trick is that as as you move this wire upwards, then the current should be slightly going upwards, and the magnetic force is also perpendicular to the direction of the current. So here it almost looks like the magnetic force is doing the work, but instead it's the battery that does the work, and it's being conveyed to this to the direction of the conveyed into the normal sorry, it's conveyed into the direction of the gravity by the force of the magnetic field, but the magnetic field actually didn't do the work. So it's like that here if you have a slope and you have a mass, and if you push the mass towards the right hand side, even though this slope is not doing the work, it's you that doing this work, the mass will actually move straight up. So in this physical mechanical problem, the slope didn't do the work, but it's actually converting the work done by you to this to the vertical direction. So these two problems are actually the same. So last, I want to mention that we have this. We just discussed the line current, and here from the line current we can generalize this to a surface current. So for a surface current, it's defined by this di over this d perpendicular. So this dimension of this k is c coulomb over seconds, and divide by additional meter. And now you can convert that to coulomb over meter squared times a meter over second. So this one, the first corresponds actually to a surface charge distribution, and the second is the velocity. So you can think of a moving surface charge will produce a surface current. And likewise, we can define a volume current. So for this volume current is the current per unit area. So we should, in terms of dimension, it's coulomb per second over m squared. Now we separate this into two terms. One is coulomb per meters cubed, and another is a meter over a second. So sorry, this shouldn't be there. Should be J equals to rho v. So here this is the charge density, and this is the speed of that charge density. So you can also think of a volume current being a moving a volume charge that's moving in velocity v. Okay, so for example, say that there is a current in a uniformly distributed that in the wire with radius a, then the volume and current density should simply be this J here simply should be I over this area, and sorry, and then this area is should be pi a square. And the second, okay. Likewise, say that the current density in the wire is proportional to the distance from the axis, and the J equals to say that equal to constant times S. Then the total current in the wire can should be able to, you should also be able to do this by integration. So I should be J d s. I'll use the so the surface. So what do we use for this unit surface? I don't exactly remember the symbols. So let's say that it's the ds is written in ds, but we should use so this unit surface is s ds d theta, and here this s it goes to 0 to a, and the theta goes to 0 to 2 pi. So it's 2 pi k integrating 0 to a of k d, sorry, integrating over s squared ds, which is 3 over 2 pi k s cubed evaluated at 0 and a, which gives 2 pi k over 3 a cubed. Okay, so the last okay, I think that should be in the previous page, but last what I want to mention is the continuity equation, but I guess we don't have enough time, so I will discuss this in the next lecture. So if you are not very familiar with what I just talked about today, so try to get a review of the chapter 10 and 11 in Physics 2041. That will help you maybe remind you about what's being discussed in the magnetic case. Okay, so that's the end of today.